Hello everyone. I welcome you all to this talk on building interactive real-time dashboards on data streams. I hope you and your family are keeping safe amid the pandemic. In this talk, I'm going to discuss the requirements of a real-time analytics stack and present a solution using a combination of multiple open source projects. If there are any questions during the talk, please keep posting them in the chat and we will take all the questions at the end of the talk. About me, my name is Nishant Bangarwa. I am the co-founder and head of engineering at Real Data. Real Data was founded with the vision to provide operational intelligence for data in motion and help organizations gain actionable insights from their data. Real's fully managed Elastic Cloud Service is powered by Apache Druid. Prior to Rel, I was part of the engineering team at Cloudera and MetaMarkets, where I helped hundreds of enterprises build their data analytics stacks. Let us now discuss an open end-to-end stack using open source technologies and build a dashboard on top of streaming data. We will discuss the challenges involved and how each component of the stack addresses those challenges. As a sample problem, let us consider Wikipedia edit stream. Whenever any page is edited on Wikipedia, an edit event is generated, which contains details about which page was edited, when was the page edited, which IP address that page was edited from, whether the page was edited by a human user or a bot, and so on. Our goal is to build an aggregated dashboard providing summary of Wikipedia edits, as shown in this picture. Let's take a closer look at the dashboard in detail. This sample dashboard provides a simple aggregated view over our Wikipedia edit stream. The information on the dashboard is updated in real time. As more edits keep on coming, the data on the dashboard is also updated. In terms of the data visualization, first, on top left, you can see the total number of edits as well as the number of unique users making changes on Wikipedia. So we can see that there are almost 3.7 thousand users and 18.2 K total edits were being made. On the top right, you can see a time series showing how edits are made over time. On the bottom left, there is a pie chart showing country-wise breakup of the edits and a date filter to filter the data based on the time range. On the bottom, there are few tables which also shows country and city-wise breakup of how edits are happening at different locations. Let's try to break down the problem even further. A sample event from Wikipedia edit stream looks something like this. First, we have the title of the page, then the URL of the page, which was edited, then the IP address of the user, and the number of characters which were added or deleted. First, we would like to consume these events as they are coming raw from Wikipedia. After consuming these events, we would like to enrich those events by adding geolocation information, which can be done by doing a geolocation lookup over the IP addresses. And we can know like from which city or country this particular IP address belongs to. Then we would like to store these streaming events in a data store from where they can be queried and finally visualized on a dashboard. So the required components of this stack are as follows. First, a solution for event flow using which we can move events from one place to another in a reliable and guaranteed way. Second, an event processing layer which can process events and transform or enrich those events. Also, this layer is known as ETL. Third, a data store that can provide subsequent queries on incoming data streams. Finally, we need a visualization layer that allows creation of dashboards on top of the data store. Users can interact with the dashboards to gain insights from their data. Now let us deep dive into the detailed requirements of each of these four components and see how different open source technologies can help solve those requirements. The first one is event flow. Event flow is used to send events from one place to another in a reliable and guaranteed way. In event flow, producers produce messages, which are then consumed by the consumers. Most commonly, this is achieved by using a message queue. Producers send messages to a queue from where one or more consumers fetch those events. The high-level requirements of an event flow are as follows: low latency and high throughput for handling really high volume of data. Failure handling in case there are any producer or like consumer issues. Need for message delivery guarantees. There, these are of three types: at least once, exactly once, and at most once. Exactly once being the most difficult to achieve. Scalability is also one of the key requirements at very high scale to handle very high volume of data. Apache Kafka is the de facto standard for streaming solution and is being used by many large enterprises and is quite proven at scale. An Apache Kafka cluster is constituted by a set of brokers. A stream of messages is stored in a topic. Topics are partitioned and distributed on Kafka brokers. The broker also replicates partitions for high availability. Producers on the left hand side produces data and write that data to topics. And consumers on the right hand side consume that data from different topics. As shown in the illustration, each message in the partition is identifiable by an offset, and ordering of events is guaranteed within a single partition. Consumers consume messages from partitions sequentially, one by one, and are also responsible for keeping track of their own offsets. So, in case there is a consumer failure, the consumer needs to know where it last read, what was the last known good offset, and it can resume from that known offset and start reading the messages again. This also helps in minimizing the overhead on the Kafka brokers. Here are some of the key features of Apache Kafka: very low latency and high throughput delivery of your data. It also provides multiple message delivery guarantees, such as at least once and exactly once. It has a reliable design for handling failures. So there is message acknowledgements between producers and brokers. Data is also replicated on the brokers in case there is a broker which goes down. Consumers can read data from any desired offset in order to handle failures onto the consumer end. So it can handle multiple producers and consumers as well. So one topic can be consumed by multiple consumer groups. It is scalable in the architecture and can handle really high volumes of data. Next, let's talk about event processing. Event processing is processing of your event to enrich those events, to transform those events as per your business rule. In terms of the requirements, event processes follows a very simple pattern: consume, process, and then produce. Event processors read messages from a source, they do some transformation on those events, and finally writes the transformed events to a destination. Transformations can be as simple as doing simple lookups, for example, replacing some IDs with the actual values. Or it can be complex aggregations, such as which involve time-based windowing or joining of multiple data streams. Failure handling is important to guarantee message delivery semantics such as at least once or exactly once. Scalability is also one of the key factors when we are talking about producing large variety of data. There are many solutions out there which support event processing, such as Apache NiFi, Apache Samza, Apache Spark, Flink, Apex, Kafka Streams, and Storm. Today in this talk, I'm going to pick Kafka Streams, which is a rich, lightweight event stream processing library. In Kafka Stream, each event is processed one at a time. Kafka Streams support both simple stateless processing as well as complex stateful operations. Complex stateful operations involve time-based windowing, joins, or aggregations. For stateful operations, state data is locally stored in a RocksDB database. For recovery, each change to this local state is also propagated to an event to a changelog topic in Kafka. In case of failure or topology restart, local state is restored from that changelog topic in Kafka. The changelog is also periodically compacted to reduce the overall size. When compared to a standard consumer, it Kafka Streams provides higher level abstraction constructs for faster application development, but it also provides less control for very fine-grained consumption. In case you need to, to get that finer level control, you can also use the low level consumer API and write your own custom application. However, that is going to take some more time. So Kafka Streams is really beneficial if you want to do fast development for your uh, event processing applications. Here is a sample code for the Wikipedia example that I used in this talk. So first, a K-stream is created from a Wikipedia raw topic. Then each raw message is passed and the IP address of the is mapped to the geolocation using the MaxMind GeoIP database lookup. Any null messages are then filtered out. And finally, the enriched messages are sent to a Wikipedia enriched topic. Now let's talk about the third and one of the very important components of the stack, the data store. The data store is one of the key elements as it takes the most of the heavy lifting of your queries and is responsible for the overall user performance that the user is going to see and the interactivity of your dashboards. So here are some of the key requirements of a data store. So any processed events, they are then stored to a data store and the data store is responsible for handling queries. For the data store, it should be able to handle streaming data and make it queryable as soon as possible so that fresh data is visible on your dashboards. It should be able to provide sub-second query latency for powering interactive dashboards. And it should be able to scale up to petabytes of data volume. In terms of query patterns, for this specific example where we are talking about the Wikipedia dashboard, we mostly need summarized aggregated data on our dashboards. So it will be good if the data store can also store summarized data instead of the raw data. The data can get huge over time, so the data store also needs to scale as our data grows. Finally, high availability is needed before we can deploy it in any production setup. For the data store, I will talk about Apache Druid, which is one of the projects I have worked extensively on. Apache Druid is quite suitable for these requirements. Apache Druid, it is a column-oriented distributed data store. Data in Druid is stored in columnar formats. In general, many data sets have large number of dimensions. Example, hundreds or even thousands of columns in a given data set. But most of the queries only need 5 or tens of the columns. The column-oriented format helps Druid in only scanning the required columns. In order to provide sub-second query times, it also utilizes various techniques like bitmap indexes to do fast filtering of the data, use of memory mapped files to perform low latency data scans from memory, data summarization and compression to reduce overall data footprint, query caching to avoid spending compute cycles on repeated queries. Apache Druid also supports real-time streaming ingestion from almost any ETL pipeline. All the query optimizations allow arbitrary slicing and dicing of the data, and you are no longer needed to create pre-canned drill downs. It also provides out-of-the-box support for data summarization. That is, during ingestion, it can summarize your data. Example, if my dashboard only shows events aggregated by an hour, we can optionally also configure Druid to summarize the data by hour during ingestion and thus scanning already aggregated data at query time. So all these techniques such as data summarization, bitmap indexes, query caching, they all improve your overall query performance. And overall, it is able to provide those sub-second query times by using all these different techniques. Uh, there is also extensive support for approximate algorithms such as hyperloglog or theta sketches, which allows you to do fast approximate answers, such as how many distinct users visited my website in last 1 month. Now you can do an exact answer for that, and it could take up to a minute, but you can also do a fast approximate answer using hyperloglog or theta sketches, which can be done in few seconds. So it really helps in both ways. It helps in reducing the data footprint when we are storing the data, because these hyperloglog objects are much smaller than storing the raw events. Also, it helps with the performance. Finally, Apache Druid is scalable and well tested in production to petabytes of data. In fact, we are still the longest running service around Apache Druid, which is at MetaMarkets, is still up and running from last several years, and my team is still maintaining that service. It is also highly available and supports features such as rolling deployments and rolling upgrades and data replication. Here are some of the suitable use cases for Apache Druid. One of the key use cases is powering interactive user-facing application, which requires high-performance queries and data freshness. Arbitrary slicing and dicing of your large data sets, where you need not tell with your pre-canned drill downs in advance when doing data modeling. You can do slicing and dicing or drill down on any of the existing combination of dimensions or metrics. Doing user behavior analysis, such as measuring distinct counts, doing retention analysis, funnel analysis, or A/B testing. Exploratory analysis or root cause analysis is also one of the key use cases, where you have your operational data ingested into Druid, and you want to know when some issues happen, what is happening in my system right now, where are things going wrong, which service is being broken. So all those kinds of answers can be analyzed on top of Apache Druid in real time, since it supports that streaming ingestion. One of the key characteristics of all these use cases is that we are not interested in dumping entire data set. However, what we are interested in is querying aggregated views over large data sets. The overall query result is much smaller than the data being scanned. Next, let's talk about Druid's architecture in little bit detail. So Druid's architecture involves multiple node types. It has a concept of each node type is designed and optimized to perform specific set of tasks. The first set of component I'm talking about is on the top, which is real-time index tasks. So real-time index tasks essentially do three things. They handle real-time ingestion. They support both pull-based as well as push-based ingestion. They handle queries. You can also, like, as along with the data ingestion, they also have the ability to serve queries on the data as soon as it is ingested in memory on the real-time index task. They also store the data in a write optimized data structure on JVM heap. Periodically, they convert this write optimized data structure into a read optimized time partition immutable segments. These segments are finally, after some point, persisted and then handed over to a deep storage. Deep storage can be any distributed file system which acts as a permanent backup of your data. In case you also need to do ETL, like data enrichment or joining multiple streams of data, you can do it in a separate ETL before sending the data to the Druid real-time index tasks. These index tasks are highly scalable, and you can create multiple of them. Next component is the historical nodes. Historical nodes are the main workhorses of the Druid cluster. They use memory mapped files to load immutable data segments. They also respond to user queries. The segments are immutable and read optimized. So historical nodes are able to serve many queries in very fast and efficient way. Now let's see how data can be queried. Since the data is distributed over real-time and historical nodes, we need a new set of nodes called the broker nodes. The broker nodes keep track of where different data chunks are located in my cluster. It has the ability to scatter query across multiple historicals and real-time nodes, gather the results back from those nodes, and then merge those results and send it back to the user. They also support a distributed caching layer where they can cache the results coming from each of the partitions in order to avoid doing repetitive calculations when the queries are repeated. Now let's discuss another case when you are not having streaming data. In most of the cases, the data is delivered on a daily basis or on an hourly basis. If you want to ingest batch data into Druid, you can also do that by batch ingestion. Batch job can be done on either a Hadoop cluster, or you can use Spark to run your batch job, or you can also use Druid native batch ingestion tasks, which converts your data into time partition segments and persists those partitions directly into the deep storage. From deep storage, those partitions are then loaded onto the historical nodes. With many real-time and historical nodes, there is also a need for communication and load balancing across them. This is done by the coordinator nodes. Coordinator nodes uses Zookeeper for coordination. They ask historical nodes to load or drop the data. They also move data across historical nodes in order to balance the load in the cluster. They also manage data replication for high availability based on the load rules. Druid also has few more external dependencies as shown in this picture. One is a metadata storage, which is used for storing information about the segments, that is the location of the segments in the deep storage, information on how to load those segments, etc. A distributed caching layer based on Memcache or Redis can optionally be also added in this architecture. This cache will be used to cache partial query results and can improve performance. Now, let's talk about our final layer, which is data visualization. Here are some of the key requirements of a data visualization. On top of a data store, we need to create a dashboards. Visualization layer can be broken down into two pieces, a semantic layer and a dashboarding layer. Semantic layer allows to define additional custom dimensions, metrics, and their associated business logic. The dashboarding layer needs to support for rich interactive visualizations. It should be able to work with multiple sources of data, allow for finer security and access controls such as row or column level security, data masking, etc. If these capabilities are not supported by the data store. Finally, visualization is an end user facing component, and every organization needs to customize it as per their own branding. So the data visualization layer should allow for custom visualization and extension for the user facing elements. For this visualization layer, I'm proposing Apache Superset. Apache Superset is a modern enterprise-ready business intelligence web application. It is fast, lightweight, intuitive, and loaded with options that make it easy for users of all skill sets to explore and visualize their data. Apache Superset is based on a Python backend, which uses Flask app builder for building the applications. It also uses SQL Alchemy for its SQL toolkit. The front end is created in JavaScript and React. It also has deep integration with Apache Druid. Here are some of the sample dashboards created using Apache Superset. You can see that these dashboards vary from very simple dashboards, which uses basic bar charts, line charts, area charts, or pie charts, to very complex dashboards using Sankey diagrams, tree maps, sunbursts, and geographical visualization. So the dashboarding capabilities in Superset is very rich. You can find almost every kind of visualization in Superset. Now let's talk about why Apache Superset for our visualization layer. Superset provides an intuitive interface for visualizing datasets and crafting interactive dashboards. It has a wide variety of beautiful visualization to showcase your data. It also provides a code-free visualization builder to extract and present datasets. This allows users who are not familiar with coding to also create their own dashboards. A world-class SQL IDE is also available for preparing data for visualization, including a rich metadata browser, a lightweight semantic layer which empowers data analysts to quickly define custom dimensions and metrics. It also has out-of-the-box support for most SQL-speaking databases via its SQL Alchemy dialects support. It provides seamless in-memory synchronous caching and queries for improved performance on the top. So overall, it provides very, very good user interface and experience for building these dashboards. But in the area of security as well, it really provides very excellent support. It supports an extensible security model that allows configuration of very intricate rules on which who can access which product features and which datasets. Integration with major authentication backends such as LDAP, OAuth, OpenID are also supported. The ability to add custom visualization plugins helps organizations customize it as per their own branding. They can also use the provided programmatic API for even embedding and extending Superset for their needs. So overall, it is like highly customizable, secure, and very provides very rich visualizations. That is one of the reasons why we chose Apache Superset for this particular talk. Now, overall, finally, in order to summarize the Wikipedia real-time dashboard example, the raw Wikipedia stream is captured using Kafka Connect and added to a Wikipedia raw topic. The Wikipedia raw topic is then consumed by a Kafka stream processor and enriched by adding the geolocation information of the user making the edit of each event. The enriched events are then saved to Wikipedia enriched topic. Apache Druid's native Kafka indexing capabilities are used to stream the enriched topic directly to Apache Druid. At last, Apache Superset is used on top of Apache Druid to create our final dashboard. Here are some of the resources of the projects I mentioned in this talk: Apache Kafka, Apache Druid, and Apache Superset. You can also evaluate and see the Wikipedia data ingested in real time on RIL's public dashboard, the link for which is given here. Thank you all for taking time to attend this session. I hope it would help in everyone with their data analytics journey. If working on open source projects is exciting for you, we are also actively hiring for multiple roles across at RIL Data. Please reach out to me on my email address nishant@realdata.com or any of the mentioned social channels on this slide. I would be happy to hear from you. Open for questions.